So I changed the title because this is not per se pacemaker experiments, and perhaps one of the outcomes of this meeting will be we need to find better definition of or use word for pacemaker and hiatus. Then that may be an accomplishment. Idealized Atlantic multidecadal variability experiments within the community Earth system model, that's CESM. So I just want to point out that this is joint work between GFDL and NCAR. NCAR part is led by Frederic Castruccio, and Steve and I are participating. And from GFDL, Johan and Rim are here, and Tom is also involved. And GFDL part of this work, and in more detail, sort of scientific part, more scientific part is going to be represented by Johan. And I think Rim is going to talk about similar restoring issues that Christophe highlighted. And with that, I'm going to essentially spend some time describing. So just a brief motivation and goals. Our primary goals are to document climate impacts of sea surface temperature, SST anomalies associated with the AMV, and we are trying to investigate associated physical mechanisms. The two groups, GFDL and NCAR, we are trying to follow a common experimental protocol. The protocol is developed at GFDL to the extent possible, and I'll highlight some of the differences that we have at NCAR. And we are perform suites of idealized AMV SST perturbation experiments using CESM1 and GFDL CM21 fully coupled models. So in addition to addressing various science questions, specific aims, especially in the early part of this study, includes assessing robustness of our results across coupled model simulations, two different systems. And I will actually talk about, focus on this particular presentation, investigation of whether tropical or subpolar Atlantic SST anomalies show the largest climate impacts. So the most important component of this work is essentially a common definition of the AMV SST pattern that we want to use in our simulations. So Ming Feng actually gave a nice presentation yesterday detailing how the AMV anomaly was created. So I skipped most of the stuff, and this is just providing a summary of that. It's based on her work. In fact, she actually provided the, I believe, AMV index. It's an updated version. Updated in the sense that the models that are being used is now the 20th century CMIP5 integrations as opposed to CMIP3 integrations used in the 2009 work. And the idea is essentially using a set of coupled model simulations for the 20th century, together with a signal-to-noise ratio maximizing EOF analysis, you estimate the forced component of the North Atlantic SST variability, then to create an index to represent the internal variability in a sense that's subtracted from the North Atlantic SST time series. Then to get the associated AMV pattern, SST anomaly, you simply regressed the observed SSTs onto the AMV index created in this way. And there is a 10-year low-pass filter involved, and if you do that, you end up with this particular AMV anomaly. So note that there are, in a sense, two distinct bands here. One is the tropical band that with an amplitude of about 0.15 in the regression, and the largest anomalies in the SST occurs in the northern North Atlantic in a subpolar gyre in excess of 0.35 degrees Celsius. So this anomaly is imposed. So we are, in a sense, this is not per se pacemaker, but it's idealized AMV impact experiments on the atmospheric circulation and land. And some of the issues that Christophe essentially indicated can be avoided by using short integrations in this case.
Can you also perturb in the Pacific, or is this just a...
Just Atlantic in this case. I'll show you the perturbation regions in a second. So we are using the Community Earth System model, CESM version 1. And it is based, the model-based version is the same as that's being used in our large ensemble pre-industrial control simulation that went for over 2,200 years. Nominal resolution in all components is order 1 degree, ocean, atmosphere, sea ice, and land. Just to indicate that we are using the Los Alamos Parallel Ocean program version 2 as our ocean component. And the CESM, the atmospheric model is the newer version. It's CAM5. As opposed to CAM4 that was used in our IPCC contribution, and it supposedly has some improvements in the atmospheric model. And it's a finite volume model. So what is the protocol? Again, I just want to stress that this is developed at GFDL, and I'm just presenting it essentially here. So AMV SST pattern is superimposed onto model's own SST climatology. The goal here is that we want to, the control case is not the pre-industrial control, but the way the experimental protocol is set up, we are essentially trying to get a similar mean state in our control as in our perturbation experiments. Over the North Atlantic, whenever there's an AMV anomaly is imposed, the coupled model is restored to the resulting sea surface temperature pattern, and elsewhere it's free to evolve. I already said that the control integration. We are using in our NCAR version daily model SST climatology obtained over a 1,000-year period. So this is slightly different from the GFDL use that will be monthly in the GFDL case. We are using 5-day restoring time scale, and I think when people talk about the restoring time scales, either we need to use piston velocity, so it's important, we can't just say 5 days, 2 days, we need to specify a length scale associated with that. So this is 5 days over 10 meters, or 25 days over 50 meters that's commonly used in oceanography community, or it should be probably expressed in terms of watts per meter squared per Kelvin or per degree C. We need to be really specific in our communication in the restoring terms. We are not using any restoring under sea ice, and I don't know why that thing appeared. Okay. And AMV SST pattern is time independent. So the experiments are 10-year long, and this is on purpose. We are trying to avoid any drifts in the ocean model, and we do not have any additional balancing that's going on in the top of the atmosphere. And based on our 10-year experiments, and we check the top of the atmosphere in balance, they are within our sort of expectations. And I just wanted to list the experiments that we performed. These are 10-year-long ensemble experiments. Control is the daily SST climatology restored case. And for each of the sensitivity experiments, there is a separate control. We have AMV plus, AMV minus. That's the AMV plus is imposing the temperature pattern that I just showed. AMV minus is the negative of that. And for the reasons that come up, become clear when I show some of the results, we are considering 3 additional experiments. AMV plus, subpolar North Atlantic. That means the AMV SST anomaly is imposed only in the subpolar North Atlantic, and I'll show the region. 3 times AMV plus subpolar North Atlantic. For again, I'll show you the results. We actually bumped the amplitude of the AMV anomaly by a factor of 3. And in the last experiment, we are using only imposing the tropical SST anomalies only in the tropical Atlantic region. And the results are going to be presented as differences from the control, and stippled regions represent 95% confidence levels. I should also mention that these are very preliminary results, and we haven't actually looked at some of the details, and I'll be showing only climatology. Ideally, we would like to do some seasonal analysis, and that hasn't been done yet. So, what are we doing with respect to the regions? The top is the AMV anomaly pattern. So when we say full North Atlantic restoring, it's essentially from 0 to 60 degrees north. And the purple region is full restoring, and we have a 7 or 8 degree transition region linearly changing the restoring amplitude. In the North Atlantic, subpolar North Atlantic, this is the region. All AMV anomaly is imposed only in that particular region. It's roughly between 45 and 60 degrees north. And in the tropical experiment, AMV anomaly is imposed between the equator and roughly, I believe, 25 degrees north. So those are the separate regions. How are we obtaining the ensemble members? So since this is an expensive integration with 1 degree CESM, we chose to go with 30 ensemble members, and GFDL equivalent is using 100 ensemble members. They have a cheaper version of their coupled system. And our initialization involves what we, well, not we, at Hawkins called macro and micro initialization. In other words, to get the 30 ensemble members, we are choosing, in our subjective opinion, 3 distinct ocean states with different PDO or PDV representation, with different AMV representation. Then each one of those is perturbed in the atmospheric model in the temperature field at the round-off level. So that's how we are creating the 30 ensemble members. But there are other ways of doing it. I mean, GFDL is following simply using their control simulation and choosing different start dates. You can do any, I mean, there are millions of ways of creating the ensemble members.
It's the same atmosphere?
It is the, no. In this, it's the atmospheric model is perturbed at the 16th digit in the temperature field. That's what it means.
What do you do
Under CIs, there is no restoring. It's just like what you showed, yeah. And do we get what we put in? And so this is AMV pattern that we are trying to restore to. This is June, July, August, September SST anomaly, and we are actually matching what we are putting in the summer months. And I should have actually followed Christoph's explanation better here. So in the winter months, DJFM, we are actually deviating from what we are putting in. And reasons include is no restoring under sea ice regions. You can see the differences. Some of the large amplitude SST anomalies occur under sea ice. And what is meant here is essentially what Christoph said, faster, more energetic dynamics in winter that's associated with deeper mixed layers, and that's why we are getting larger, we think, deviations in the restoring. So in terms of drift, I'll just show you one sort of metric here. When the integrations are 10 years, the changes in the ocean model are not as large or significant as Christoph showed. But if you continue longer, and I think Johan or Rim is going to show this, then the drifts are going to become an issue, then you have to really worry about that. So what is shown here is the control and AMV plus SST RMS errors. So in the control, we have the daily climatology, for example. We know what the SSTs we are restoring to, and that's what the model is producing. So there's clearly some seasonal cycle. Some ensemble members deviate in the winter months as much as 1.5 degrees. Mean is in the black. This is the AMV plus experiment. Mean is also in the black. And our conclusion from that thing was essentially, we are not just this metric, other metrics too. Over a 10-year time scale, we can live with whatever the drift is, and the drift is really minimal in this measure.
What's the variable you plotted bottom line?
These are Labrador Sea average root mean square differences in the SSTs.
Just in that one region?
Just in this upper region right here, in the Labrador Sea region. Just as a metric. We have done other regions too. So, just to show you some results, I'll start with the AMV plus AMV minus experiments. These are just showing the sea level pressure, 10-year climatological composite, 30 members. And this is AMV plus experiment. This is AMV minus experiment. So you can see that, and then this, you can see that this is the sea level pressure anomaly associated with the negative phase of the PDO. And you get pretty much the opposite in the AMV minus. Not just from this, but other fields, when you look at these, we seem to be getting really opposite and almost linear response between AMV plus and AMV minus. So from now on, that's why we focused initially only on the AMV plus experiments. So I'll show you those experiments next. Okay, starting with the SST, and you can ignore the pretty much what's, this is not showing anymore. This is not showing it either. Anyway, so yeah, we need a real pointer. So what is shown here now, and I'm going to use the same formatting here. AMV plus subpolar North Atlantic, 3 times the AMV plus subpolar North Atlantic, and AMV plus tropical Atlantic. So you can see where I'm going with this. With the AMV plus experiment, we are seeing actually a negative PDO type of response in SST. If you just apply the SST restoring in the subpolar North Atlantic, there's pretty much no response anywhere else. If you increase it by a factor of 3, just to see whether we'll get any response or not, you can see a large, you can see the perturbation there, and we start to recover some of the PDO-related response that we see in the Pacific Ocean. But I was a bit surprised, maybe this is expected. You can see that just by restoring in the North Atlantic, this region, and the temperature anomaly, that's what I was trying to convey, is rather small. It's of the order of 0.15 degrees Celsius. And yet the response that you get is almost, in fact, larger than the full AMV response that you are imposing in the experiments. Surface air temperature. Surface air temperature, so you can now ignore on this plot the land, ocean areas, because that's going to be very similar to what I showed earlier. And you can see a large land response 2-3 times the AMV pattern imposed only here. But you pretty much see that the tropical Atlantic SST anomaly imposition actually recovers more than the full AMV response. And one interesting thing is that, are we getting anything close to observational sort of land temperature changes? And you can see that you have cooler temperatures over Africa, North Africa, and warmer temperatures in the sort of southeast US, and that's consistent with the observational estimates or observational data, and you recover that thing surprisingly only for the tropical Atlantic AMV signal. It's not surprising. Okay, Gokhan says it's not really surprising. Tropics is everything, which is showing the case, I guess. Sea level pressure, I've shown the AMV plus earlier, and it's essentially the same story right now, and I'm just trying to show you other fields. One interesting thing is that you can see the response in the Southern Ocean. I'll come back to that in a second. Okay. Precipitation. The general response is that in all of the cases, we are seeing northward or poleward shift of the ITCC. And again, the largest response occurs with the tropical Atlantic SST anomaly. In terms of 10-meter winds, enhancement of the easterlies in the tropical Pacific region. One thing that was interesting to me is that essentially enhancement of the winds also in the Southern Ocean, and particularly in the tropical Atlantic case. As an oceanographer, I have no idea what that means in the wind, so that's why we are looking at the wind stress that the ocean is going to feel. These are now plotted such a way that the directions are also shown where these changes are significant. But it's interesting that this is actually increased zonal wind stress along the Southern Ocean latitudes. This increase has direct impacts on the ocean heat and carbon uptake. So that is going to be an important impact of the remote impact of the tropical Atlantic SSTs. Okay. I have no idea what this is. I just thought that, I know what it is. It's U100 zonal velocity at 200 millibars, but I don't know how to interpret it properly. The point that I was going to make here is that there seems to be some wave train coming from here, and you can see that thing in the tropical Atlantic pattern as well. And finally, the storm tracks, the field that I'm showing here. This is meridional velocity perturbation at 500 hectopascals, and I'm told that this is a common metric that's used to measure storm tracks. With the pure, this is AMV plus again, you can see enhanced storm track activity there. With the just North Atlantic, you are actually seeing a decrease of the storm activity. Whether you do 3 times or not, it doesn't matter, but with the tropical Atlantic, you are seeing enhancement both in the North and Southern Ocean. So, one final plot for the ocean model. These are showing the AMOC changes in these experiments. Again, the goal here is essentially avoid changes in the ocean, go short so that we can avoid drifts and any other issues. So AMV plus, there is some reduction I mean, these results are not surprising at all. I mean, if you impose higher temperatures, you're going to get some weakening in AMOC. Just subpolar North Atlantic, it's very similar in that response. Now, in this case, see the 3 times AMV is going to AMOC, particularly ocean circulation, simply because you are changing everything or density structure in the northern North Atlantic in the Labrador Sea. Tropical Atlantic, as expected, the change in AMOC is really minimal. Okay. So we have designed an experimental protocol to assess climate impacts of AMV, again idealized, and to understand the physical mechanisms, and Johan is going to talk about it more. Not this afternoon, it's tomorrow now. Sorry. It's going to be tomorrow because there's shift of schedule. Okay. Your talk is tomorrow too now. So. And so preliminary results indicate that the tropical Atlantic is the first order impact of the AMV. Not a surprise, perhaps, or a surprise. AMV plus and minus lead to negative PDO, and this is not necessarily a new result, the second bullet. Other impacts include poleward ships of tropical precipitation, stronger zonar winds in the Southern Ocean, and many others. And we are thinking, I mean, it's going to be resulting from teleconnection changes in the atmosphere, these remote influences. And again, as I said, our NCAR efforts are very preliminary. We are going to do more analysis of these, but this is just a first cut at the results, and more in Johan's and Rim's talk. That's it.
Thank you very much. Questions? Yes, for that.
So, lovely set of experiments. Thanks, George. Lovely set of experiments. So much in there. That 3 by subpolar perturbation, to me it looks like anything coming still, there's still there's still a tropical Atlantic forcing to that.
Which field are you talking about?
So the bottom left panel.
Yeah.
Just the fact that the tropical Atlantic warms there.
Right.
May still be the main driver of the.
That exactly. Yeah. I forgot that. That's a good point. In fact, you remind me that I should have actually said something else as well. That's a very good point. I forgot to mention that. The second point that I wanted to make is that with the tropical Atlantic response of the sea level pressure, you see actually an AO-like response in the region that we are not actually restoring to. So that's another important feedback, I think.
Yeah, I agree. And so the second thing I was going to say quickly is the Southern Ocean response is fantastic. If you go back one slide to the SAT fields, maybe the air temperature.
Yeah.
So what is amazing here is you've got this result with the tropical Atlantic. So the bottom right panel, you've got the Ross Sea sector cooling and the warming of the peninsula region. That gels with a couple of studies out last year, which shows this teleconnection from the tropical Atlantic down to the Amundsen Sea low. So it's deepened over time, and if you force AGCM experiments with that signature, you get Simpkins et al. In John the Climate and Ding et al. In Nature.
Thank you.
John, Jerry, John?
I didn't have to.
You did?
I could have a quick question. The Southern Ocean wind, it's hard to judge how big that anomaly was.
Well, it is actually that's what in terms of the wind.
Yeah.
It is roughly 5% of the wind stress. I mean, the anomalies are really small. Right.
Yeah, so go back to the SST one. Yeah, that one. So this, I guess you're interpreting this as a chain reaction, right? So you specify the tropical Atlantic, that affects the Pacific convective heat anomalies, affects connections into the Southern Ocean.
Right.
Yeah, because I think there's evidence that if you put in a positive convective heat anomaly over that SPCZ, positive precipitation anomaly, you're going to get that teleconnection into the Southern Ocean. So that's probably.
We need to look at it more. Yeah, those parts are not done.
Once the Pacific kicks in, then everything's going to follow that.
Okay, everyone?
Gokhan, I think it's an important point that the extratropical SST anomalies don't have much signature over the land areas. And that's probably the explanation when you look at the scale of the decadal predictions. You see the scale in the SST, but the land areas is mostly
I mean, one thing
Right.
that I did not stress enough is essentially, I just highlighted the temperature. If you look at the precipitation compared to observations, the tropical Atlantic anomaly case is actually matching the observations much
Right,
better
but
than any of the
not
cases.
not the extratropical SSTs.
Right.
They don't
Yeah.
lead to much response. So.
So I think the question still remains of what's the mechanism of forming this tropical SST anomaly when the biggest changes due to AMOC, for example, are in the subpolar charge?
Yes, I agree. I agree.
If there is an atmospheric bridge, why don't we see it here?
Yeah, I mean,
We only see it when we make the anomaly very,
Yeah.
very strong. So.
My question really follows on to that. So you showed changes in the AMOC as well, which presumably are not realistic. So my question is really, is that weakening of the AMOC, is that affecting the tropical Atlantic response such that any forces we may have got from the North Atlantic is being cancelled out?
we can take a look at it. I mean, the thing is that, I mean, we need to do more stuff with this thing. We need to divvy it up. These are 10-year segments that I've showed. I mean, we can look at it first 5 years and the next 5 years. My sense is that the fact that we are matching the SST anomaly initially in the yeah, I mean, I can answer your question, just to, yeah, to be brief.
Okay. Any final questions? Yes.
Just a comment to what Arun said. In the experiment we have done, like similar to what Gokhan presented, we used 100 members with respect to 30 here, and we find that actually the signal increases over land for some. When you look on seasonal, so there might be more hope to find some signal over land. And 30 members might not be optimal for all the region and the signal we'll look at, and also this tropical response, when you look at the first 5 years, doesn't seem to be contaminated too much by the bias, but then if you look at too long, like 10 years or 20 years, depending on the model, then yes, you can be contaminated.
Okay, thanks very much, Gokhan. Thanks to all of our speakers.